Hello everyone, Dr. Terry here, and we're going to talk about inverses and inverse matrices in this video. So the definition of a invertible matrix is an n by n matrix for which there exists a second n by n matrix that when you multiply them together in either order, so my original matrix was A, my second matrix, my new matrix is B. If I multiply those two matrices together and I get the identity matrix, and that's what an inverse matrix is. Those things do exist. Typically, we denote the inverse in the usual way for inverses is A superscript minus 1. And yeah, so you take a matrix, you multiply it by another matrix, and you get the identity matrix. And for reasons we'll talk about, they've got to be square matrices. So here's a quick example. I'm not going to go through it, but the deal is if you multiply the matrix 2, 1, 1, 1 by the matrix 1, minus 1, 2, together you will get the identity matrix, a 2 by 2. So I've got a 2 by 2, 2 by 2 equal a 2 by 2 identity. A couple of important things about inverse matrices is that the inverse of a matrix is unique. There's only one matrix that works with the original matrix in this way, and that's actually, it probably lines up with your experience, but that's also true here. Some other terminology that you'll see is another standard term for an invertible matrix is a non-singular matrix. And then similarly, if a matrix does not have an inverse, it's called singular. And so, I always thought this was funny that we have these two definitions, or kind of two sets of terms, invertible, non-invertible, singular, non-singular. It's just, in some sense, in both cases, one gets a word and the other version gets a non-word. You just negate the word to get the original. So invertible, if you're interested in matrices that have inverses, that's the word you use. And a non-invertible matrix is a singular matrix. Singular matrices do have their own interesting properties that we'll kind of talk about. And yeah, we'll get into that later in the video. Okay. So some quick properties of invertible matrices. One is, like most inverses, they come in pairs. And so the matrix, A has an inverse. It's invertible, so it has a matrix A inverse. Well, that is an invertible matrix as well, and its inverse is the original A. So, A is the inverse of A inverse, and the inverse of A inverse is also A. Again, you have seen that before with functions, and even with negatives. The negative of a negative is a positive. The reciprocal of a reciprocal, the multiplicative inverse. That's what a reciprocal is. They come in pairs. All right. Also, if you multiply two matrices together, and you want to talk about the inverse of that matrix, it exists, but it's the inverses in the opposite order. If you think about it, this actually makes pretty good sense. When we talk about inverses, you can, sometimes you can think about it as doing things, even when you're multiplying matrices, multiplying by one matrix, then multiplying by a second matrix. And often, one way of thinking about inverses is as like undoing that original something that was done. So multiplying by a matrix to multiply by the inverse of a matrix is to undo that original multiplication. And when you do things in sequence, sometimes to get them undone, you have to reverse them in the order in the reverse order of what you did them. I like to think about like putting your socks on and then putting your new shoes on. When you take those, take your shoes and socks off, you take your shoes off first, and then you take your socks on. So again, to reiterate, the usual way: socks on first, shoes on second. To undo that, shoes off first, socks off second. So again, it's a reversed order. And again, if you goof that up, things are going to get weird. A couple of other properties. Remember, one of the things we talked about with matrices is that, hey, it's possible to have, like A times C times A times D, with C not being equal to D, and that's just one of those curious things. Well, if you have an invertible matrix, that you can do. Honestly, all you got to do is algebra here. Is since a matrix exists, take that AC is equal to AD equation, apply the inverse on the left side, the inverse and the A make an identity. You get C all by itself. The inverse and the A on the other side make an identity, so you got D. So you can really just, because you have an inverse, you can use that as an algebraic property. You can basically cancel it off. Similarly, we talked about the fact that invertible matrices, that you can multiply two matrices and get 0 with neither matrix being a 0 matrix. If A is an invertible matrix, that is no longer true. That, again, just do the apply the inverse to both sides of that equation. The A will cancel off, and the C has to be 0, because any matrix times a 0 matrix is a 0 matrix. So again, one of those things about invertible matrices is they kind of act in ways that you're used to, like more like real numbers. Like when you're dealing with real numbers, you can cancel. Everything has an inverse. And same, when the product is 0, then one of the factors is 0. So that's kind of saying, like, with invertible matrices, you're getting kind of into a more familiar situation with what you're used to. Okay. Now, one of the things we've talked about earlier is that linear transformations are functions from one Euclidean space to another Euclidean space, Rn to Rm, and they preserve addition, they preserve vector addition, they preserve scalar multiplication. That's right. And then we talked about the fact that though the linear transformation can always be written as a matrix, and as a matrix multiplication, and so that's kind of where we're headed next. And so, but at its most basic, a linear transformation is a function, and so if it's one-to-one and onto, then it has an inverse function, and just the usual function stuff. If your original function takes vector x to vector y, then the inverse is going to reverse that match and take vector y back to vector x. That's just standard function stuff. There are a couple things that we need to say about this. The first is when you're talking about linear transformations that are invertible, they have to go from Rn to Rn. Those ends must match, because if you ever try and make a linear transformation to between Euclidean spaces where that doesn't match it, that linear transformation will either not be one-to-one or not be onto, and you have to have both those properties to be able to invert the matrix. Invert the linear transformation. The other thing is, while T is, as a linear transformation, is a function, and it has an inverse function, since the original T preserved vector addition and scalar multiplication, the inverse does too. And so you can think of it as a function, but it's the original thing had the original linear transformation had those special properties. The inverse has those special properties too. And then finally, this is kind of where I was headed with that matrix business, is if you write your linear transformation as matrix multiplication, it turns out the inverse linear transformation is just multiplying by the inverse matrix, and so everything works out pretty much the way you'd expect it to. Okay, all right. Now, if you have a matrix and it has an inverse, and you want to find that, actually the simplest way to do that is to make I guess this is an n by 2n matrix. And so in the first part of the matrix, you put your A matrix, you put your square matrix for which you're trying to find the inverse, and then you put the identity matrix in the second half of it. And it turns out if you take that particular matrix and put it in reduced row echelon form, so just row reduce it, you'll end up with the first matrix being an identity matrix, and the matrix in that second part will be your inverse, and you can multiply A times its inverse, and you'll see, oh yeah, that works out. The reason for that is, remember how we talked about that row operations correspond to elementary matrices, and so all elementary matrices, as it turns out, are invertible. I may show you that in the example problems. And when you multiply a matrix, like when you multiply that matrix by a row, by an elementary matrix, basically you're going to multiply that A by it, and then you're going to multiply that identity matrix by it. That's actually effectively what happens. And in some sense, by moving that A toward the identity matrix with all these elementary matrices, you're really just kind of going through the step-by-step process of inverting it, and it's the second half of that matrix sort of keeps track of those elementary operations, and so ultimately you've multiplied that A matrix by a bunch of matrices to get the identity. So the product of all those things, which is just being kept track of in that second, that's going to be your inverse. And it really does work out. We'll definitely work an example of that in the example problems. Okay, quick theorem that if you have an n by n matrix, and then you've seen these equivalency theorems before. So there's three statements that are equivalent. First is A is an invertible matrix. The second is, if you form that that system of equations using the matrix, so matrix A times vector B is equal to matrix A times vector X is equal to vector B. That has a unique solution, and the solution is pretty much what I was talking about before. Apply that inverse to both sides. If you apply it to A times X, the inverse and the A form an identity matrix. You get your X by itself. And on the right-hand side, you have A inverse B, and that's actually just one quick way to solve a matrix version of the system of equations if you happen to have the inverse handy. Similarly, if you have the homogeneous system, A times vector X is equal to the 0 vector, that only has the trivial solution. It really kind of lines up. Again, you can do the apply the inverse to both sides algebraically. The trickiest thing to see here is why those other two lead to the matrix being invertible, but it is provable. And so I refer you to the textbook if you would like that to see that justification. Okay, we'll wrap up this video with a unifying theorem. We saw this back when we talked about spans and linear independence. And then earlier, then after that, we talked about linear transformations and how the transformation being onto or one-to-one kind of lines up with this as well. Well, now we've got the idea of an invertible matrix, and we're just kind of adding to our list of things that are equivalent. And so we have a set of vectors, all those A's there. We have the matrix that has all those A vectors as columns. And then we have the linear transformation, that is that A matrix times X. And all these things are equivalent. So if one of them is true, they're all true. And that is that that set of vectors spans all of Rn, that set of vectors is linearly independent, that the matrix version of that system of equations has one solution, a unique solution, equivalent to the linear transformation being onto, equivalent to the linear transformation just being one-to-one, and it's also now equivalent to that matrix A being an invertible matrix. And so that's just kind of, if you know one thing, that tells you lots of things about a given situation. I think later we'll talk about like the flip side of this unifying theorem, where instead of everything being nice and invertible or one-to-one or onto or independent, that you can flip it and say, well, if I got a singular matrix, if I'm non-invertible matrix, then all this other stuff, the kind of the flips of all these things are also coolly equivalent. All right, so that's just a quick overview of inverses of matrices. Head to those example problems, work some out, and just get some practice with this idea. And I'll see you in the next video.